Alright, so welcome to this week's workshop, everyone. This week we're going to be talking about block ciphers. So, what we're going to look at today, we're going to start with just a brief overview of encryption and the basics of block ciphers, and in particular we'll take a look at AES. Then we'll look at block cipher modes of operation, what those are and how some of them work, and we'll take a look at some different attacks we could launch against block ciphers. So we'll start with just a brief review of what encryption is. Basically, encryption allows us to send information without it being visible or understandable by someone who it's not supposed to be. So if we want to send something to someone else, we can encrypt the information, then anyone who sees it in between shouldn't be able to understand what it is. And there are two main types of encryption. There are symmetric crypto systems where both the parties involved, or both of the people who are involved in communication, are going to have the same key. So encryption and decryption are both done with the same key. We see in the example here, you have private key. It should be private to only the people who are supposed to have access to the information. We use that for encryption or decryption. And then there are also asymmetric encryption systems, and in these there's a public key and a private key, and we can tell the public key to everyone, but we want to keep the private key to ourselves, and then anyone can encrypt something with the public key, but only the private key can be used to decrypt it. So that's a quick overview of encryption. So now we'll look at what block ciphers in particular are. So basically, block ciphers are just an encryption algorithm that works with data in fixed size blocks. So for example, you might have an algorithm that takes a block of 16 bytes and encrypts that. And there are a bunch of different block ciphers. I mean, anything that acts on a block of data could be considered a block cipher. There's stuff like DES, AES, the Advanced Encryption Standard, or the Rindell cipher is pretty much the most common one that you'll see nowadays. So AES, this is a symmetric cipher, so remember that means encryption and decryption use the same key. So how does AES work? Well, it takes 16-byte blocks from a message, and then it does some math. Well, it generates a bunch of round keys and does some matrix transformations and XORs some stuff, and basically a bunch of mathematical wizardry. And what we need to know is we're just going to treat AES as basically a black box. So if we give it a plaintext block and a key, if we give it the same block and the same key, we get the same ciphertext. Or if we're decrypting, we give it the same ciphertext and the same key, that gives us the same plaintext back. And that's all we know about it. We don't really know anything about these values other than if we run the algorithm, we get the other one. So now we said there's a bunch of fancy math, but of course complicated doesn't necessarily mean secure. So how secure is AES? Well, it turns out quite secure. We can technically do better than brute force, but realistically it's not enough better that we can actually break AES realistically. So that algorithm that we mentioned, it's fairly secure, but there are some other problems, and we'll see those in a little bit. So now we have quick challenge here to get a feel for how AES works. There's a program, decrypt block. So basically all this is going to do is going to take an input in hex, and it checks that it has the right block size, which is 16 bytes or 32 hex digits, and if it does, it decrypts it and prints the result. And there's a ciphertext in the file, ciphertext.txt. These are all posted in workshop materials, in case you didn't see that. Yeah, and that ciphertext will have a few blocks, and you'll just have to break them up and run them into this program. You might not have the libraries you need to run this program, so you can also connect to it with netcat. And yeah, if you just type this, you can basically interact with it like you would a normal Python program. And I'll give you a few minutes to work on that. Let's just go through how we would do this. So let's pull up our ciphertext here. So we see our ciphertext is just string and hex. This is going to be more than one block here. So we'll just count out one block, which remember is 16 bytes or 32 hex digits in AES. So that'll be our first block. Let's just enter netcat. Oops. Make sure I enter the port number. So we give it their ciphertext for that block. It prints out the first block, and then just go back to our ciphertext. We'll take the next block, feed it in, next block. And yeah, that's basically what we have to do for this challenge. Okay, so let's move on here. Okay, so before we get into more stuff in block ciphers, do a quick review of XOR. So remember, XOR is a bitwise operation, and it's described by this table. Basically, when you can XOR two bits, if they're the same, so they're both 0, they're both 1, you end up with a 0. And if one of them is 0 and one is 1, you're going to end up with a 1. And that's basically how XOR works. We'll need this later on. So now we're going to get into modes of operation. So what do we do when the plaintext isn't just a single block? Well, we just saw this a little bit ago. So we can, assuming it's not a multiple of the block size, we can pad it so that it is, and then we can divide it into blocks of whatever the block size of the block cipher is, and then we can just encrypt each of those blocks. But it turns out we might not want to do this. This might cause problems. It might not be clear why right now, but it turns out we might want to do a bit more than just chopping it up and encrypting it. So modes of operation are basically different ways of dealing with encrypting multiple blocks. So yeah, we might do something on top of just splitting it up and encrypting it, and we'll see this is what these describe. So the first mode of operation, and this is what we've seen already, it's ECB or electronic codebook mode, and this is the mode of operation that just splits blocks up and encrypts each of them separately, and that's all it does. So we look at a graphic of this, basically we just take our plaintext, we split it into blocks, we run it through our block cipher algorithm, and that gives us the ciphertext blocks. We just put these together, and that's our ciphertext. And yeah, that's basically the simplest mode. That's how ECB works. So I mentioned there could be problems with this mode. Well, to see this, let's think about what happens when we use the same key and the same plaintext. Well, the result is going to be the same ciphertext. We talked about this earlier when we were saying that we're treating our encryption algorithm as just a function. If you give it the same inputs, it's going to give you the same output. So as an example, you'll see this picture in a lot of places if you're reading about block ciphers. Yeah, so we have this picture of tux and encrypted using ECB mode, and we see that if the pixels are the same in the original picture, well, we encrypt them to the same thing. And the result is that we can still see most of the original picture in the encrypted version. So this means that anyone who is trying to attack this can gain quite a bit of information about what the original plaintext is. Because, yeah, if there are patterns in the plaintext that are the same, well, yeah, now the person who's trying to break the cipher knows that part of this plaintext is the same. And if they know what that is, then they gain even more information. So now we'll look at another mode of operation that tries to fix this problem. So first one we'll look at is cipher block chaining. So rather than just encrypting things, before we encrypt a block, we XOR that block with the ciphertext of the previous block. So that means we're not actually entering the same input into our encryption function. So even if the plaintext blocks are the same, the encrypted blocks are going to look different. So as a graphic here, we have, see we split our plaintext into blocks like we did before, and then we, for the first one, we'll choose initialization vector. This should just be a random string the same length as the block. And we XOR our plaintext with that and encrypt it. And then to encrypt the next block, we don't just encrypt it, we first XOR it with the ciphertext from the previous block that we encrypted. Then we encrypt that, and that gives us the ciphertext for this block, and we just keep doing that for each block. And basically that's how CBC mode will work. So there are a bunch of other modes we could use. We're just going to look at one more, and we're going to look at counter mode. So it's another way we can try to deal with this problem of having blocks that look the same if the plaintext is the same. But it's going to be a bit different than the last two modes that we looked at. We don't actually apply our block cipher algorithm to the plaintext directly, per se. So instead what we're going to do is we're going to choose a nonce, which should be a random value, and we're going to concatenate it with a counter. In this counter we're going to increment for each block, and then we take this value, we encrypt that, and we XOR that value with the plaintext. So we'll look at a visual to make this hopefully a little bit more clear. So you see, yeah, we're not just, well, we do split up the plaintext into blocks again. You see them down here, but what we do is we choose a random nonce, and that'll make up, like, say, half of our value here or whatever. And then we have a counter which we increment for each block, so we concatenate those together, and then we encrypt this value. And then we take the encrypted value for each block and we XOR it with the plaintext block, and that gives us the ciphertext. So in effect what we're doing here is we're kind of turning this block cipher into what's called the stream cipher, which basically just means you have a stream of bits and you XOR that with your plaintext to get the ciphertext. And that's pretty much how counter mode works. So that's all we're going to look at for modes of operation. Well, now we're going to see how we can actually attack these. The first fact we're going to look at exploits a quite poor security practice, but you might see this sometimes. So suppose we're using some application and it's encrypting something in counter mode, but instead of generating a random key and random knots, the key and knots are hard-coded in. So how could we take advantage of this fact? So remember counter mode, we just talked about this. Basically what it does is XOR the plaintext with some key stream that it generates using the knots and the key, basically. So since the knots and the key were reused, there are a couple properties of the XOR operator we can use if we have a plaintext ciphertext pair to effectively break the encryption of any other pairs. So the first property of XOR that we're going to need is if we XOR something with itself, this gives us a string of zeros. We can just think about it as, remember how XOR works. If we XOR 0 with 0, well, that gives us 0. If we XOR 1 with 1, that gives us 0. So if we XOR something with itself, we get zeros. And the other property, if we XOR something with a string of zeros, then we're going to get that same something back. And same way, think about that. If we XOR 0 with a 0, we get 0. If we XOR 0 with a 1, then we get a 1. So we just get the same thing back. Yeah, so using these, we can XOR a plaintext and a ciphertext that correspond to each other. And that'll give us the key, basically. Or the key stream, I guess you could call it. And once we know that, we can just use that to decrypt any ciphertext that was encrypted using the same key in IV. So just to show how the math works, so remember that the ciphertext is basically just the plaintext XORed with the key stream. So if we XOR a plaintext with the corresponding ciphertext, well, the plaintext basically zeroes itself out. Then we're XORing 0 with the key stream, so we get the key stream back. Then we XOR this with another ciphertext that was encrypted with the same key. Well, then that key stream is basically going to zero itself out, and that just leaves us with the plaintext that corresponds to that ciphertext. So now we have another challenge here. File CTR same key txt. That's going to have a plaintext, corresponding ciphertext, and another ciphertext, and you're going to want to find the plaintext for that one. And yeah, these were encrypted in counter mode with the same key in IV. So same example we've just been working through. If we take a look at this file, so we have our plaintext here. Then here, these are just pad bytes. If you're using Python, you can just enter these in a string, and each of these is basically like a character, but it's not a printable ASCII character. And yeah, then this is the corresponding ciphertext, just given in hex. XORing it can be a bit of a pain. You can try using some online converters, or Python. Well, I'll work through like some of the Python commands and whatever you might need. So I want an ASCII library. So let's start with, say we have string, and yeah, we can just enter the pad bytes like that in the string. To convert this to bytes, we can just do, well, we can just do that. Or, whoops. Sorry, we need to encode the string as ASCII first. Just call bytes on that. So, and that'll convert that to a byte string, which we'll need to XOR it later. Then if we have something in hex, we can just use this function. So this is, it's not clear, but yeah, this is going to be a hex string. And yeah, so we print that. We'll just get another byte string, and then we can just XOR this byte by byte. And you can just iterate through a loop to, or something like that, or whatever you want to do to XOR each character, and then to convert that value to a character, we can just use the CTR function. And in this case, it's not anything legible because we just made these strings up, but yeah. And hopefully that should be everything you need to actually do this. So, go back here, and I'll give you a few minutes to try this out. Alright, I think we'll just work through this. Hopefully we can not leave everyone too sucked, but okay, so actually let's just leave that running, and we will pull up the file here. Okay, so first let's just convert everything to bytes so we can work with it in Python. So plaintext here. Okay, so that'll encode our index as bytes. And for ciphertext, yeah, that's our plaintext there. The first line. Okay, so now we have our plaintext and our two ciphertexts. So we'll just gonna do this in one shot. Okay, so or I'll just write this out and explain it. Okay, so basically what I'm doing here is I'm iterating through each byte and, well, each of the plaintext and the ciphertext. So When we XOR a plaintext byte with the first ciphertext, these plaintexts and this ciphertext, they correspond to each other. So when we're XORing these, that's basically doing this step here. That gives us the key stream. Then we take the key stream that results from these, and we're going to XOR it with the second ciphertext, which is basically this step. So that will give us back the second plaintext. And yeah, so we just iterate through all the strings, and yeah, it gives us the flag you can. If we want to print this out as a string, since we have an array of characters here, we can just join this thing, and yeah, that gives us a flag. Oh. Oops. Can you see that better now? Hopefully you got that down, or at least got a rough idea, maybe. I think we're going to move on to the next attack that we're going to look at here. So, yeah, we've mentioned this earlier when we were talking about ECB mode, that there were some issues with ECB mode, which basically the problem is if we have the same plaintext and the same key, well, we wind up with the same ciphertext block. So turns out if we can control part of the plaintext, even if we don't know everything that follows it, we can use that to figure out what the plaintext is following that part that we can control. And this is a chosen plaintext attack, so this is what we're going to work through next. So we'll work through sort of an example to hopefully get a feel for how this attack works. So start by supposing we have some piece of data and it's encrypted using a block cipher that has a block size of 8 bytes. And there's going to be a name field that we can control and a flag field that we don't know and want to find out. So as a visual here, we have basically the parts in red. These are just parts of the string that we know and we can't do anything to control those. Then this orange here is the name field, and this is a value that we enter into whatever the program we're working with is. And then this blue part, we don't know what this is, but we want to find it out. And you see this split up into blocks of 8 characters or 8 bytes. So how this attack works, the first thing we want to do is line up the blocks so we know all but one character of the block. So we're going to know all but the last character of one block, and then we want to remember the ciphertext of that block. So in this example, we can, if we enter 2 characters, just whatever here, we don't care about what this block encrypts to, then we can line this up so we know the first 7 characters of the second block, but there's 1 character at the end, and we don't know what this character is. We just know that it's the last character in this block, and we know the rest of it. And we want to remember the ciphertext of this second block, and we're going to need to use this later. So where we go from here is we use characters, just enter whatever to line up the blocks. We can enter known values from the string and brute force the last character. We'll have a visual here so we can see this a bit more clearly. So we do the same thing we did before. We enter a couple of characters, so now we don't care about this first block. So everything we type after these first 2 characters, this is what we care about. So we're going to enter the values that we know are at the beginning of that block that we recorded earlier. So we know these first 7 characters, and then for the last character, we're just going to guess something. And the idea is we'll keep guessing this character. So we guess that this character is A, and that's not right. So we're going to have to make another guess. So we make a guess that this last character of this block is going to be a B. Well, that's not right either. And then when we happen to guess that this last character is an S, now something interesting is going to happen. It just so happens that in this example, the third block lines up so that this is the block we're trying to guess. Or you can do that, or you can use the ciphertext that we took note of earlier. So we see that when we guessed S, the ciphertext of this second block is going to be the same as the ciphertext of this block. So that tells us that the plaintext of these blocks are the same. So then we know that the first character of this value that we were trying to find is an S. And basically, for the rest of the attack, we're just going to repeat this same process to recover the entire secret. So, and the next time, or the next iteration of this, we're going to line things up again. We enter, there's 6 characters this time that we already knew, and then now we know what this S is. So we can enter this, and then we're just going to guess values for this last character. We can guess A, B, whatever. When we get to E, then ciphertext of this block is going to be the same as the ciphertext that we take note of when we line things up, entering values to line it up so we want to have everything from there to E the block. I'm going to take note of the ciphertext of that. And then, we brute force values until we find a match. And that tells us a second character that we don't know, and we can just keep doing that until we've recovered the entire secret. So, now we have a challenge where we're going to carry out this attack. And yeah, the program that you'll be connecting to is shown in this file. So let's pull that file up. Put it in the chat here. Okay. Never mind. Okay, back to this. Okay, so we have, this is a file that, the program that you're going to be working with. So what it's going to do is going to take some data as input, and it's going to put it into this string. This is similar to what we saw before. So we know this part of the string and this part. We control the data that goes here, and then we're trying to find the flag, which will be in this part of the string. So after it puts our data that we give to the program into this, we're just going to encrypt that using ECB Mode. And remember, the block size for AES is going to be 16 bytes or 16 characters. And yeah, the program is just going to print out the ciphertext in hex. So if you actually want to completely solve this, you're going to have to code it. I'd recommend, before you jump straight into that, just try to get a feel for how it works. So line things up. So for example, you know the flag starts with UCSec, the first character is going to be U. Try to line things up so that U is the last character in a block, and then try to, well, I guess just enter a block that has a ciphertext that matches that block. And then you know you've found that block, and you can use a similar process to find the rest of the flag, like UCSec, and then you can use it to brute force the flag. And also, the flag for this challenge only contains lowercase letters, underscores, and brackets, just so there's not as much space to brute force. And yeah, I guess I will copy the code. This is how we connected to the first challenge using netcat. This shows how you can use pwn tools in Python to connect to it. So basically, you just some import setup stuff, and you can connect to the IP and the port. Then each time you want to interact with the program, you send it with that, and yeah, and then you'll have to open a new connection each time. And I'll post this into the chat so we can jump back to another slide, and you can start working on that. Give you some more time to work on this, but first I want to go through just like what I suggested, finding the first character of the flag, just so we can try to get a feel for how we can approach this. Okay, so open this up, and so let's take a look at what we want to enter here. So we'll start by counting out how many characters are in this first part. So see there's going to be 14 characters in this first string. So if we enter 2 characters here, we're essentially going to have this string and 2 characters is just going to be the first block, and we don't really care what the ciphertext of it is. We're just line things up so we can actually do what we want later on here. So now we want to try to match the block where the last character is the first character of the flag. So we want to count back 15 characters here. So 4, 5, 10. So that'll be, we have 15 characters here. And those in, and say we don't know the first character of the flag, we know it's AU in this case, but say we're trying to brute force it. So enter last character here, and then this is 16 characters, so this is going to be a block, and this is a block that we're controlling, and we're trying to make it match one that we're going to have later on. So we want this to be the beginning of a block so we can compare against it later. So we see we have 3 characters here. We need to enter 13 characters of just whatever. And that means our third block is basically just going to be some garbage and up to here. And then the fourth block is going to be this one. And this is the block we're trying to match. That's the one we're interested in. So yeah, that's just hypertext. Go like that. I'm just going to split that up so it's a bit easier to read. So we see in this case, our second block and our fourth block, well, they're different. That's because we guessed wrong. We guessed this character is A, well, it's actually a U. So now let's try this again. Now, if we didn't know the character, we'd be brute forcing values. So let's see what happens if we. So sorry, it's not anything fancy. It's basically just splitting up these blocks so it's easier to read. The output's exactly the same, it's just on multiple lines. I can show you the file. So yeah, all it's doing is taking the output from the program, and yeah, it just splits it into blocks of 32 digits and prints those out. Okay, so if we enter our payload again, but in this case we're guessing that the last character is EU, so we're guessing correctly. And you see in this case, the second block of the ciphertext is the same as the fourth block of the ciphertext, which means the second and the fourth blocks are the same. So we've found the character we wanted to find. And yeah, and then you just want to use a similar process for the rest of the blocks. And so I'll give you, this is the last challenge we're actually going to work on today, and then we'll actually go through the solution and wrap things up. But if you want, you can go into breakout rooms or whatever and try to work on this challenge for a while longer. Alright, so yeah, we'll take a look at the solution for this problem. Okay, so first thing we do, we just do some setup. that's just our character set for flag. Then we'll go through how we actually solve it. So essentially we're just looping, well, through different shifts of the string and then through the characters and open up our connection, and then the payload. This is kind of the interesting part. Is so if we look at how it works in the first iteration when I is 0, it's going to be similar to the example I worked through before. So we add a couple characters, and that's going to round out our first block, and then we don't care what that is, and then we have 15 characters before the flag, and this will be empty to start, and then here we have, it's going to be a character, and we're going to iterate through different guesses for what this character is. So basically this is going to be the second block, and that's one we're trying to control and look at. And then we have I have 29's A's here, which is essentially there's just going to be 2 blocks of garbage before this block appears again. I don't think you probably could have made that 13 rather than putting an extra block in there. I think I was just going to try to code this all in one loop at first, and then decided it would be easier to split it up. But yeah, so basically you brute force values for that character. We check if the second block is equal to the 5th block now, just because of how I line things up. And if they are, we know we found the right character, so we can add that. And then next iteration in the loop, we're just going to, well, we're going to toss out this first character. And now we have 14 characters here plus 1 that we found, and then we're brute forcing the last character again and lining things up, and we compare those blocks, see if they're the same, and basically repeat that to find the flag. And then the second loop here is doing the same thing. It's just that, well, the flag is longer than 1 block, so that we just had to change up the alignment, and we're just brute forcing in the same way in this second loop here. And yeah, that's pretty much the solution to this problem. So we'll just wrap up the presentation here. So I just wanted to mention there are other attacks you could launch against block ciphers. One that's I think is fairly important. We're not going to go over it today, just in the sake of not overwhelming everyone more than I might have already. Yeah, so padding oracle attack is an interesting attack against block ciphers, and it works against, we didn't see how to attack this earlier, but it'll work against cipher block chaining mode. And there's an appendix in the slides on padding oracle attacks and another challenge on that. I'll post it later for anyone who's interested in all that time I'm sure you have between midterms. And yeah, so that's everything for today. So just a review of what we've looked at. So we've seen what block ciphers are and gotten a sense of that, and we've looked at what modes of operation are, and we've seen how some different modes work. We looked at ECB and cipher block chaining and counter mode, and we looked at a couple attacks on them. So, and yeah, you can keep working on, I'll probably stick around for a while, and you can keep working on challenges we did earlier, or I'll post the slides in a couple minutes, and if you're really interested, you can try reading up on padding oracle attacks. And yeah, that's the workshop for today. So I guess good night, everyone, if you're heading out, or I'll stick around for a little bit.